The finite volume method is a method for representing and evaluating partial differential equations in the form of algebraic equations. LeVeque, 2002. Toro, 1999. Similar to the finite difference method or finite element method, values are calculated at discrete places on a mesh geometry. Finite volume refers to the small volume surrounding each node point on a mesh. In the finite volume method, volume integrals in a partial differential equation that contain a divergence term are converted to surface integrals, using the divergence theorem. These terms are then evaluated as fluxes at the surfaces of each finite volume. Because the flux entering a given volume is identical to that leaving the adjacent volume, these methods are conservative. Another advantage of the finite volume method is that it is easily formulated to allow for unstructured meshes. The method is used in many computational fluid dynamics packages. 1D example, consider a simple 1D advection problem defined by the following partial differential equation. Here, represents the state variable and represents the flux or flow of. Conventionally, positive represents flow to the right while negative represents flow to the left. If we assume that equation represents a flowing medium of constant area, we can subdivide the spatial domain into finite volumes or cells with cell centers indexed as. For a particular cell, we can define the volume average value of at time and at time as, where and represent locations of the upstream and downstream faces or edges respectively of the cell. Integrating equation in time, we have where. To obtain the volume average of at time, we integrate over the cell volume, and divide the result by, that is. We assume that is well behaved and that we can reverse the order of integration. Also, recall that flow is normal to the unit area of the cell. Now, since in one dimension, we can apply the divergence theorem, that is, and substitute for the volume integral of the divergence with the values of evaluated at the cell surface of the finite volume as follows. Where. We can therefore derive a semi-discrete numerical scheme for the above problem with cell centers indexed as, and with cell edge fluxes indexed as, by differentiating with respect to time to obtain. Where values for the edge fluxes can be reconstructed by interpolation or extrapolation of the cell averages. Equation is exact for the volume averages. That is, no approximations have been made during its derivation. This method can also be applied to a 2D situation by considering the north and south faces along with the east and west faces around a node. General conservation law. We can also consider the general conservation law problem, represented by the following PDE. Here, represents a vector of states and represents the corresponding flux tensor. Again we can subdivide the spatial domain into finite volumes or cells. For a particular cell, we take the volume integral over the total volume of the cell, which gives. On integrating the first term to get the volume average and applying the divergence theorem to the second, this yields. Where represents the total surface area of the cell and is a unit vector normal to the surface and pointing outward. So, finally, we are able to present the general result equivalent to, that is. Again, values for the edge fluxes can be reconstructed by interpolation or extrapolation of the cell averages. The actual numerical scheme will depend upon problem geometry and mesh construction. MUSCL reconstruction is often used in high-resolution schemes where shocks or discontinuities are present in the solution. Finite volume schemes are conservative as cell averages change through the edge fluxes. In other words, one cell's loss is another cell's gain. See also, finite element method, flux limiter, Godun's scheme, Godun's theorem, high-resolution scheme, KIVA, MIT general circulation model, MUSCL scheme, Sergei K. Godun, total variation diminishing, finite volume method for unsteady flow. References, Emad, R. Gorlauer T. R. Herbin, R. The Finite Volume Method Handbook of Numerical Analysis, Vol. 7, 2000, pages 713-1020. Editors, P. G. Kylett and J. L. Lyons. LeVeque, Randall, Finite Volume Methods for Hyperbolic Problems, Cambridge University Press. Toro, E.F., Riemann solvers and numerical methods for fluid dynamics, Springer Verlag. Further reading, Paytanka, Suez 5, Numerical Heat Transfer and Fluid Flow, Hemisphere. Hirsch, C., Numerical Computation of Internal and External Flows, Volume 2, Computational Methods for Inviscid and Viscous Flows, Wiley. Laney, Culbert B., Computational Gas Dynamics, Cambridge University Press. LeVeque, Randall, Numerical Methods for Conservation Laws, ETH Lectures in Mathematics Series, Birkhauser Verlag. Tanhill, John C., et al. Computational Fluid Mechanics and Heat Transfer, 2nd ed., Taylor and Francis. Wessling, Peter, Principles of Computational Fluid Dynamics, Springer Verlag. External links, The Finite-Volume Method by Arimard, T. Gorlauer T. and Herbin, update of the article published in Handbook of Numerical Analysis, 2000, Ra 1/4 Benker paragraph Nig, Oliver. The Finite-Volume Method an Introduction. Archived from the original on October 2, 2009, available under the GFDL. FIPY, a finite-volume PDE solver using Python from NIST, Clawpack, a software package designed to compute numerical solutions to hyperbolic partial differential equations using a wave propagation approach.